Chapter 22, Example 4. A company has set a goal of developing a battery that lasts over 5 hours, 300 minutes, in continuous use. A first test of 12 of these batteries measured the following lifespans in minutes: 321, 295, 332, 351, 281, 336, 311, 253, 270, 326, 311, and 288. Is there evidence that the company has met its goal? So we want evidence. Again, we're going to do a hypothesis test. As before, I have all the data in a calculator document, so you can go ahead and put it right in there. Let's start by defining our variable here. So let mu, which is our population mean, equal the mean time in minutes that batteries last. We haven't done this previously, but I want to start getting in the habit of defining the variables. It will make things easier in the future. Okay, so H naught is that mu equals 300. So we're saying our population mean is 300. The alternative is that it is greater than 300. The batteries last longer on average than that. So H alternative is that mu is greater than 300. That is what we're going to test. To the conditions. We do not have a random sample, but it is reasonable to think the 12 batteries are representative of all batteries the company makes. "12 batteries are fewer than all batteries made, and the normal probability plot is fairly straight with the data close to the line." And here is that normal probability plot. Just without the data typed in the calculator, we just do the normal probability plot in Unitlist graph, and there you go. The conditions are met. I will use a student's t-model for a one-sample t-test with 11 degrees of freedom. Just as before, we'll use the calculator to get all statistics. There we have all our data put in. So we'll go to our handheld. We have the data there in a column. Time is the name of it. We're going to do a new page, a calculator page. Of course, we'll go to Menu, Statistics, Stat Tests. We want a t-test, and we're using the data that's already typed in there. 300 will be our population mean. The list is time. We want to make this greater than 300, and then hit OK. All our data is there. T is 0.738661, the p-value is 0.237789, degrees of freedom 11, gives us our x-bar, our mean, 306.25, and the standard deviation of our sample, which is 29.3106. So x-bar, the mean of our sample, is 306.25. Our standard deviation is 29.31. T, with 11 degrees of freedom, is 0.739. Our p-value is 0.238. So now we're ready to state our conclusion. my p-value of 0.238 is large, and I will fail to reject the null hypothesis. There is not sufficient evidence to suggest the batteries last longer than 300 minutes. We don't need to do a confidence interval there because we didn't reject the null hypothesis. Find a 90% confidence interval for the mean lifespan of this type of battery. So we have all our statistics there. The mean, well, the standard deviation are 29.31, and the degrees of freedom, 11. So we're going to go to the calculator and do this. Go to statistics, interval, we're going to do our list as time. Change it to a 90% confidence interval, hit OK, and there you go. The lower is 291 hours, upper is 321. Our ME is 15.1954. Still 11 degrees of freedom. Okay, so our ME is 15.195. Go ahead and put that data in there. Write down our statistics. So our confidence interval is 291.055 to 321.445. I am 90% confident that the batteries last between 291.06 and 321.45 minutes. If we wish to conduct another trial, how many batteries must we test to be 95% sure of estimating the mean lifespan to within 15 minutes? Now this gets pretty complex. We don't have a sample size, so we can't find the degrees of freedom. Go at it in a roundabout way. We're going to find a z-score and use that to estimate our degrees of freedom, and then work back again to find out what our sample size should be for a t-test. So we know our standard deviation is 29.31 of the sample, and we want an ME of 15. So we're going to solve a sample size with a normal model. (15 equals 1.96 because we want a 95% confidence interval) will equal 29.31 over the square root of n, which is how we find our standard error. Divide the 15 by the 1.96, and we get 7.653 equals 29.31 over the square root of n. So we rearrange that, we multiply the square root of n over to the other side, divide by the 7.653 to get that square root of n alone. We have the square root of n equals 29.31 over 7.653. 7.653. So the square root of n and that 7.653 just switch places. It gives us the square root of n equals 3.82987. And of course, to get n, we just square both sides. So n equals 14.67. So we would need 15 batteries to estimate the lifespan within 15 minutes if we were using a normal model. But we can't use a normal model. We want to use a T. So we're going to redo this using 15 minus 1, or 14 degrees of freedom. So T of 14 equals 2.145. We find that from the T table. $15 equals 2.145 times 29.31 over the square root of n. If you notice, this is going to be all the same stuff we did for the normal model, except we've replaced the 1.96 with 2.145. So I divide the 15 by the 2.145. We get 6.99301, which equals 29.31 over the square root of n. So we should get a larger sample size than we had previously. Switch places with the 6.99301 and the square root of n. And we get square root of n equals our 29.31 over 6.99301. And I'm just preserving all these decimal places till the end where I'll do the rounding. The square root of n equals 4.19133 and n equals 17.57. So we need a slightly larger sample size with this T model. Now we'll state that conclusion. We would need to sample about 18 batteries in order to estimate the mean battery life to within 15 minutes with 95% confidence.